you, I think Winston's going to show some slides and talk about, show some links to PDX data, so I won't mention that. But so in future meetups, the next one is 9th of May, if you haven't seen the site yet. Andrew Bray is going to talk about collaborative coding with GitHub and RStudio Server. All of June is no meetings. The next one is going to be July 12th. And so we're probably going to have 2 shorter talks. One of them is going to be Jim Walther, and I think the topic is analyzing A/B test data in R. So, and then I think I might actually give a short talk, if you don't mind, on sort of higher level DSL for HTTP requests that I've been working on. So we have a call for proposals. If you on Twitter, you've probably seen it in the stream. I'll, I don't know, put a link up somewhere. And I don't know if I can put it somewhere on the meetup site, but anyway, I'll try and get it out there. I'll send an email around. And so if you have an idea for a talk you want to do, pop it in there. If you have an idea for a talk you want to hear, or like a sort of a style of a type of meetup you want to attend, then put that in. Yeah, and we're going to go to a local watering hole. Whoever wants to go after, just self-organize after the talk. So Winston is going to talk tonight, and I actually don't know all of his affiliation stuff, so I'll let him introduce himself.
Hi. Winston Saunders is my name, and one of the prerogatives of being the speaker is changing the title. So, Unsupervised Politics, Machine Learning, and R. The new title. They want a little bit of a bio, so here you go. I'm a reformed physicist. I used to have a job that I loved and didn't pay. Now I've got a job that pays. I work at Intel. I work currently in security technologies, so actually a pretty cool area. It has actually a lot of overlaps with the data science stuff that I'm interested in, so that's a nice thing, although I don't work on it right now. My history in this area is I've actually been a lifelong analytics person. I don't ask, but I used to use Mathematica, and for whatever reason. And yeah, believe me, I saw some pretty badass differential equations in Mathematica. And the last big analytics problem I did was looking at the correlation of earthquakes and drilling in Oklahoma. And it was a pretty fun little problem, but I realized quite quickly that I was out of the mathematics league, and started looking around. I found the Coursera stuff at Johns Hopkins. I said, well, maybe I can do that. Turned out to be a lot harder than I thought, but I did make it through there. Been cranking on R ever since. So that's sort of the history. Scott, do you want to hit this piece?
Yeah. Yeah. So I mentioned this last week, but just iterate again. So the R meetup is part of the PDX data sort of umbrella group of meetups in Portland, and we're sort of a umbrella group with a theme of sort of data science, data wrangling, data, et cetera. And I think the Python group is part of it. Is that right? It might not be actually. No, it's not. Yeah. And then a few other groups. And so there's information there. There's a Slack if you want to join, invite yourself. We have a website, and it's sort of the idea is to sort of share some resources among the sort of data science-y meetup groups.
Great. Yeah, and this meetup's been great. So if this is your first time here, I encourage you to participate. I've really enjoyed this group. All right. Thank you to Mozilla for hosting this. It's nice to have such a great accommodating space and gracious hosts. Let's just talk. So this is, I think Andrew Ng is like an unheralded hero. So I'm just going to make a little pitch for him before I get started. He's got this full. I don't know if everybody know Andrew Ng? He's deep learning machine and all this stuff. Like, dude's a rock star. And, you know, he has this thing I read in Huffington Post that just inspired me so much. It's like, if you spend a whole Saturday studying rather than watching TV, there's almost no payback on that, right, in the short term. But if you do that week after week, month after month, year after year, the effects can be profound. And that's sort of the way I feel about my experience working with R, right? I don't get paid to do this. I just love it. And I spend my, like last night, anyway, I spend a lot of time at it. Not a lot, I spend a lot of time at it, and to be honest, and although I won't admit to it in mostly public settings. And, you know, it's great. And you know, I'm actually pretty close to the end of my, you know, my career. But for young people, I think the world is changing so fast. You have to be able to spend the time to regenerate your ideas all the time if you're going to stay apace with what this world is coming with the introduction of AI. I just think it's a competitive disadvantage not just to learn all the time. My 2 cents. So let's talk about the agenda. We're going to go through candidates as bags of words. Adequate representation, it turns out. We're going to talk about representations of those bag of words. We're going to meet analytics, and then we're going to ask the question, is artificial or any kind of intelligence possible in politics? And then I think what I'll do is try to rush through the slides a little bit, and then just open up the code and show you sort of what the coding I did is. This is an R user group, so we should talk about practice as well as outcomes. And you know, I'll show you the rocky spots in the code. You know, where I'm sort of struggling a little bit with how do I make this work faster, and some of the hacks I had to do to make pipes work, and all the junk that I've just been futzing around with. So that's sort of the agenda. So data practice. So the first thing I want to talk about is just what I did to get the data. You know, that's an essential part of the process that people often overlook. This was a pretty simple process, not too complicated. The focus here is the text of presidential debates. What I'm really trying to do ultimately is make a Twitter debate bot. So what I want is I've done a lot of work with Twitter using R before, and I realized, you know, if I could make a Twitter debate bot. So what I want to do is be able to read a Hillary tweet, respond like Bernie, and read a Bernie tweet, respond like Hillary. That's sort of the vision that I've got. And to do that, I realized quickly that I wasn't going to just be able to do just a simple Markov chain, right? That's not a good way to start off. So I said, well, what sources of data can I use? And I thought debates would be a great format, right? That they're kind of, there's a Perry and things like that, and I thought that might be a good source. Turns out the debate text is available. There's a project called the UCSB Presidency Project. It's got lots of text of presidential stuff in there, and you can just, you know, I just click on the screen, select, copy, paste into, in this case, into Apple Pages, and I save it as a text file. That's all I do, and that's the raw data. Here's a sample of what that looks like. So let's talk about bags of words. Bags of words is the simplest text analytics. It's also very appealing because it's visual, and you know, R's got some great utilities. I made my little contribution to R by doing called candidate word clouds, which is like a 3-line modification of the standard R function. But you know, already you can see stuff, right? So here's a picture of Hillary and Carly Fiorina. I wanted to compare 2 females, and you can see right away that the stuff that they talk about is different. And you can see this through lots of the candidates, but I just picked this example as one. You know, Hillary's big word is think. She talks about people, know, going, well, president, need, blah, blah, blah. And Carly seems to just talk about government. And and the government knows, and it wants to tax, and it needs, and it's every, and whatever. But it's, you know, there's already some context even in these word clouds of the presidential debates, and it's actually pretty fun to look at. You know, my thing was I wanted to change the colors, so I changed the colors, and then I just used the word clouds with the stuff that's below, and it's actually very quick to do. There's some surprises, though. It turns out not everything turns out like you'd expect. One of the big things that's happening this electoral season is what I'd call populist revolt, right? Big parties are going away, and these usurpers are coming up and actually representing the voices of at least a subset of the population. And you know, when I looked at Donald Trump and Bernie Sanders, man, their word clouds looked a lot alike. You know, it's really surprising. You know, is it just the language? But you know, this idea that, you know, the people and the country are going in some place and they think and they know, and this idea that maybe things aren't going the way people want. I mean, I'm reading in too much there, but I found, and this persisted from debate to debate. If you aggregated all the debates, it obviously persisted. And, you know, I thought that was sort of an interesting outcome already, that there's sort of populist candidates seem to have a slightly different take, at least in the vocabulary, of the way they were describing the problems or proposed solutions to those problems for the electorate. I filtered out, yeah, I did a little bit of filtering. Yeah, there is some filtering here, and we can actually look at what that filtering was. I also, yeah. Anyway, I was going to make a joke, but I'm not going to do that. This is being published. All right, so let's get into a little bit. The problem with word clouds is they really don't, I mean, they're not quantitative. So we're going to now go into a little bit more of this understanding of what's going on and then look at the data a little bit deeper. So first thing I did was I took all this stuff that they did, all that they said, and started counting. And what this table represents is a sort of the order of words used by all the candidates in rank order, and then the counts of words by individual candidates, the number of times they said those things. So, for instance, the word people is the most frequently used word of all. Bernie Sanders said the word 162 times in 4 debates. Ted Cruz said it 24 times in 4 debates. The word tax, is tax on here? Yeah, tax is on here. And Donald Trump said it 9 times in 4 debates, and Ted Cruz said it 51 times in 4 debates. Some big differences in the way these guys talk about what's going on. This table is a little hard to digest, but you can collect some summary statistics. So I like this function in R where you can like type the text below. And you know, Hillary had a vocabulary. I think this is damn funny. Hillary had a vocabulary of 2,500 words when she spoke in the debate. Donald Trump's vocabulary is about half of that. and you know, it. Well, yeah. So there is a slight bias, and I'll actually talk. To be so you just ruined my punchline with some actual facts, but well, yeah, no, this is supposed to be data fun, not data science, and we'll talk about, you know, if you've ever studied linguistics, you know, there's a thing called Zipf's law, which is totally empirical but totally works. And you know, to be fair, there's a logarithmic relationship between how many words you get to say and the vocabulary you get to use. And because there are only essentially two Democratic candidates in equal time, they get to say a lot more. And that's really part of the bias. It's not the whole bias, but it's part of that bias going on. But it ruins the punchline if you add that fact. I still think it's funnier to say that Hillary has twice the vocabulary as Donald Trump. You can ask any question you want. Yes. I didn't do any stemming, but we're gonna, at the end of this talk, I'm gonna rip open the code and we're gonna drill in, and you're gonna. That is correct. That is correct. And I have done the other analysis, but I don't like the way it looks because it kind of looks goofy. So if you know what's going on, it doesn't bug you, but it bugs me. So yeah. So I'll talk a little bit about those. Yeah, I don't know if I have that data. I did actually look at that association, but I did do a little bit of bigram stuff, and I'll show some results there. And excuse me. Let me think here. Oh, so yeah, and the code. I'll provide all the code so you can you know, get it right. I'm not. I like to bias things. So one of the fun things, one of the little fun projects I had was trying to create a heat map. So this is actually this turned out to be a super useful tool for me, because as I started going into the word vector analysis that I'll talk about in a minute, one of the things I like to do is block out the text. So pick a subject, get rid of the stuff that doesn't apply, and then you can sort of see how the different candidates really talked about a given subject. It turns out, but this is all the data. You know, so I've normalized the word counts to the total counts by the candidate. So this is a normalized frequency of speech for each candidate, and the color scale on the right is you know, proportional to the actual frequency. The median is very far down in the noise. So that midpoint there represents about the 95th percentile, just an FYI. Distribution is very non-uniform. There's some interesting stuff already here. You can look at the word, so right in, I'm going to get off camera for just a second. You can look at the word people. And you can see everybody talks about people except Ted Cruz. Okay? Who talks about tax? Well, tax is talked about by Carlo Rubio and Ted Cruz, but almost nobody else. There's a bunch of it. It's actually a fun thing. I mean, it's fun to look at this. Obama has talked about nobody except Ted Cruz. Government is talked mostly about by Carlo Rubio and Ted Cruz. They don't mention a lot, but it's clearly one of the show up here. The country, again, everybody but Ted. It's interesting, right? You can really see that there are fundamental semantic differences in the way people are speaking about the country, or about, you know, in their actual debates. And you can do lots of drilling in with this technique here. This is just sort of the overview picture, but gives an idea of a nice visualization of the data. And you know, ggplot is obviously fantastic for this stuff. And I'll show you the code to generate this. Zipf's remarkable law. I just think this thing is incredible because it shouldn't work, and it always does. People familiar with Zipf's law? What that is? So if you take a text, a big text, and tokenize it, and then just count the number of times each word occurs and rank those, it turns out the frequency of the word is inversely related, usually linearly in a logarithmic sense, to the rank of the word. The frequency and the rank are inversely related. So if you just take a plot, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and take the frequency data and use those as the ordinates of the axes, you get a straight line. And I thought, God, there's not very, usually you apply that to, millions, if not billions of words of text. And I said, well, I'm going to try it for this candidate speech just to see if I can see anything in the data. It turns out not to be very useful, but if you take the aggregate, you can see here, I mean, the law is, it's just remarkable. It works. And so I just think it's one of the facts of nature that I'm fascinated by. It doesn't really mean any, it's hard to interpret. The one interesting thing about this is that the exponent is different, and I don't know why that is. It may have to do with the fact that I've done a little filtering of stem word or of stop words and things like that. But the exponent here is minus a half rather than minus the traditional -1, and I don't know why that is. It could be that it's a systematic error of the way I've analyze the data, but it's still a fascinating thing. If you look it up on Wikipedia, you'll see that there's one graph in there I think that applies to like, I don't know, a dozen languages, and it just works for all languages. And anyway, it's a very interesting thing. Is that right? See. Yeah. It's there's something hidden there. Yeah. Anyway, it's an
in exploratory data analysis, John Tukey lines of that and then shows the residual and talks about how, this is all very meaningful. We've learned a lot about the data, but he never said exactly what he learned.
Yeah. So that's where. So I actually tried a similar thing. It didn't mean much. I'll show you a little bit of the data that I got. But what I wanted to do was say, here's the overall aggregate. Turns out it's a pretty simple behavior. Can we learn anything from individual? So the idea here is we're trying to explore differences in candidates, right? And understand, can we understand the differences in what they're saying with different analytic techniques? Does Zipf's law give us a basis to compare candidates? Yeah, that's a great suggestion. I don't know what the why. I'll show you the code, and if you figure it out, it'd be great. So what I did was I took the individual candidates and plotted their Zipfian law-ish plot. And, you can see a little bit here, but it wasn't really very useful. You look at the Democratic candidates, Hillary and Bernie, and you can see their words vary around what you consider to be the sort of the mean trend, but there's a lot of variation. What you do see is that as you get out in rank, so about the 1,000th word or so, these are logs, so about the 1,000th word, actually these might be log base e's. Now that I think about it, I better be careful. As you get up to log 3, there appears to be quite a bit of noise. It's actually probably not noise. It's probably meaningful differences in the usages of words, but it sort of gives you an idea of where the differences really are. And the frequency variations there are quite big, a factor of 10 to the, e to the -2, so whatever that is, so about 6 or 7. So pretty big variations. In the Republican side, Ted Cruz appears much lower in even the high frequency words, again highlighting the differences in his speech, and again a lot of variation or maybe noise down in the lower ends. It's hard to tell. But Zipf's law is a standard tool, not too useful here, but there does appear to, there may be fruit for some deeper investigation if you wanted to get further into it. Another bag of words sort of thing that I did was bigram tokenization. And there were some interesting things here. I just picked one example of sort of how you could look at different contexts. So this is the word wall, what appears with the word wall. The title of the graph shows the sort of the grep thing that I used, just looking for expressions that started with the word wall. And Bernie, it's either street or streets. So he's talking about wall, street, presumably. Trump, it's Mexico, China, works, will, the wall will work. And I think the context here starts to become clear. He's talking about a different kind of wall than Wall Street, and that sort of comes out here. The bigrams don't pull out the context that you might think as strongly as, but partly limited word choices here. We're counting 1 or 2 instances, and it's not a huge amount of statistics. So candidates as bags of words. The problem with bags of words is that you're really limited in context. You're just looking at nearest neighbors, and it's hard to get a lot of intelligence out of that stuff. So I was bemoaning this, and a friend of mine said, well, I said, I'd love to try word vector analysis. There just isn't enough stuff there to really do the deep learning model well. And he said, Stanford published these pre-computed word vectors. GloVe word. Has anybody looked at the GloVe word vectors before? Yeah, they're pretty fun. And so I was like a kid in a candy shop when I found those. And so now you're going to, I remember I said reformed physicist. Now you're going to get some of that now. So that's where this is going. And you're even going to have a picture with some thetas in it. So get ready. Vector representations of words using pre-computed GloVe word vectors. So let me give you the cartoon version of how these things are computed. There's tons of blogs on how these are computed. There are really two bigger picture. There's really 2 competing sort of word vector analysis things. There's the Google word to vec, and then there's the Stanford GloVe word vectors. I was joking today that I'm losing my memory faster than my hair, but I can't remember. One of them is sort of quadratic, and the other is linear. The computational times are different to reduce these things. They're both essentially unsupervised learning, optimizing a quadratic objective, and but they're computed differently. One runs faster, takes more memory. Run one's longer, takes less memory. And I don't know if do you remember which is which, or? So that's what, yeah. So that's what I think GloVe work. Yeah, I think GloVe. Yeah. So that's what. Yeah, that's right. But ultimately, they're both solving the same problem. They just have different. They just operate differently at a computational level. There are many examples. One of the things I was trying to do last night, I think I'm just going to give up on it, was to get, anyway, I wanted to get the code I'm going to post in GitHub to actually download the GloVe vectors from the actual GloVe zip file. We'll talk about that. But the ones that I picked are just the simplest ones. They're computed from 6 billion tokens, so a ton of words, 400,000 word vocabulary. They're actually word vectors that are much larger. It's just, I'm running on a MacBook Air. The training objective tries to ensure that the dot product between 2 vectors is the logarithm of their probability of co-occurrence. So if you've ever done the Markov chain type of thing where you take the log, and it's sort of the same objective, but this is using a neural network and deep learning to look at co-occurrence across broader spectrum of words. It associates the ratios of co-occurrence probabilities with the vector difference in vector word space. So we're going to look at the cosine. I'm just going to look at the cosines of theta now. You can also, it turns out there's other meaningful information in there, but I'm just, to simplify things, I normalize everything in a unit vector and take the dot product. It includes lots of weird ass shit. Like commas and I mean, you'll see some crazy stuff come up. Yeah. Yeah. I mean, there's some crazy words in there that you wouldn't necessarily. It's kind of like the. Have you guys been following Deep Drumpf? Deep Drumpf. You know, it's this kid. He's ahead of me, but he's an undergraduate. So he used deep learning. He actually took Donald Trump's speech, and instead of looking at words, he looks at individual characters and uses a model that actually is trained on individual. So it has no idea of the concept of words. It just builds them out of letters. And it's on Twitter. You can follow it, and it's pretty funny. It's at Deep Drumpf, and this is sort of the same thing, right? Comma, like I think in some of the examples I showed, W period appears. Maybe that's George W. Bush. I don't know. There are other things that appear like comma and T, and it interprets those as word units, even though they're not what we'd consider normally words. And I think that's part of. Yeah, 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 yeah. See, throw it all in. Yeah, exactly. Yeah, yeah, yeah. Yeah, 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 and that's sort of you know, there's your tokenization. Yeah, exactly. That's the stuff that we should be more open about, I think, because ultimately that biases the outcome. That's why the question you asked at the beginning was exactly right. Yeah. Yep. And that's part of what I'm finding too. And, you know, I'm going to show you results, and you're going to, you know, reproducibility and all these things are very subjective, and this is hard stuff. And
Winston, here's a real low-level question. What's that Twitter account?
At Deep DEEP Drumpf DRUMPF, I think. Yeah, I think that's it. And he's got another one. I think it's I think it's Bernie. And I don't know what Bernie's is, but they're pretty funny to follow. Anyway, this is what the glove vectors do. This sounds pretty formal. What I did was download a zip file. So what are word vectors? So the first thing I did when I downloaded these things was I just reproduced a few canonical examples. So has anybody played or yeah, I mean a couple people have. So so the idea is word vectors work on the basis of context and association. So one of the canonical examples is think about the country England. Its capital, London, the country France, and its capital, Paris. And, all right, countries have one association with lots of other things about them, and capitals have lots of. So one of the canonical examples for word vectors is, let me get this right, England, let's see, England, plus London, England minus London plus Paris is, it turns out to be very close to the word France in a word vector space. And if you think about that, it sort of makes sense, right? You take a country, subtract one capital, you add another, and that's the way this sort of thing works. And it turns out that works with glove. I worked on the word king, so this is another canonical example. King, man, queen, woman. Those have associations, and you can sort of establish a pseudo-king vector by taking the vector for man, adding the word queen, and subtracting the word woman. And that makes a kind of a pseudo-king. And so this first graph, these are just visualizations of the actual word vectors. And what do those word vectors tell you about? Nothing, right? They're completely abstract. And that's because they're optimized by a machine for a machine, from a machine and to a machine. They don't mean anything to us. The glove vectors that I downloaded, they're 300 dimensions, 200 dimensions, 100 dimensions. It turns out, when I do all the math, the dimensionality of the matrices matters. There's a lot of subjectivity here. When you start getting results, and you're like, oh crap, what did I? It turns out I built a lot of machinery just to keep track of the experiments I do, because if I don't do that, I very quickly lose track of what I've actually done. And but here, you look at these vectors, and at first it looks like gibberish. But let me just point out a couple things here, and then we'll go into a little bit deeper picture, or a little bit shallower picture of this stuff. So I'm just going to point out. So here we have the basis. These are all the basis vectors. This is man, queen, and woman. What we want to do is take a man, add regality to it, queen, but then subtract the femininity. And that should give us something close to a king. Does that sort of make sense? You have to sort of believe in it, maybe. but you're going to believe a lot more. This is not religion. I think I'm getting punished for walking away from the mic. So I mentioned the word religion, and God starts punishing me. So what's going on here? Oops. Let's see. I'm giving away the answers. There, back. There we go. So let me see. So I think I get it here. So we got king, and let's just focus on this little tranche here. All right. So we've got man, queen, and woman, right? And they're all, you can see, so the structures in this specific area of the vector is different. This is just like the, 200 element of this 300 element vector. And the color just is, the value. King is very different here. But it turns out you take these things and you add them together and you get something much closer to the structure that you see for king. It's pretty remarkable. And you can see a lot of that stuff. There are places, let me see, when you get inspired, you can actually see places where times, anyway, it's a remarkable thing when you start really digging into it. How does the machine do that? I mean, this is the sort of mystery of the nonlinearity of deep learning, right? It's semi-empirical. These are the different structures for the 300, 200, and 100 dimensional vectors. You can see that the vector families have very little in common. It's not like the 300 vector is just, or a 100 vector is just an average of the nearest neighbors of 300s or anything like that. They're very different outcomes for the models. What you can do is plot these things. So you can take the vectors for man, woman. Here I've female, male, aunt, uncle, queen, king. And I've just sort of, this is the reproduction of sort of one of the figures that they show in the glove vector paper that shows how the vector addition might work. If you seem to be having trouble here, there we go. if you have a, you take a man, so the idea is you take man, you draw the vector to queen, that's the addition of man plus queen, and then the vector man to woman is an up arrow, but you're subtracting it, so you flip it over and subtract it down from queen, and you end up pretty close to king. At least visually, that's how that looks. And that's sort of an intuitive picture of how the word vectors look. How did I do that from 300 dimensions down to 2? It's actually like one line in R, turns out, just principal components. That's all I did. And so it took me like frickin' 4 months. No, it didn't take me 4 months, but it took me, it took me a while to figure out how to do that. But it's actually very simple. I'll show you the code on how to do that. And I use that trick quite a bit with the word vectors. But principal components work pretty well. Now the problem is that principal components, you got 300 dimensions collapsing down to 2. You're losing a lot of information. So you got to be careful about how you interpret them. They're not always 100% fidelity. They can mislead you, but when you get the right answer, it's a good way to convince people you know what you're talking about. So that's what I'm doing. How do you know you got the right answer? You use more data. And so some of the data that I've been using, this is an example. Excuse me, sorry. Is I looked at the dot product of the pseudo vector, pseudo king. Pseudo king is man plus queen minus woman, pseudo king. And then I just took the dot product with the word king. Now, if you take the dot, and I normalize everything, remember? So if I take king.king, everybody, king.king, unit vector, what's the dot product? 1. Vector with a vector, two vectors align perfectly, dot product is 1. If they're completely orthogonal, what's the dot product? 0, because it's a cosine of theta. If they're up, it's -1. So that's how dot products work. And the first thing I did was I took dot product of king.king, 1, okay. Well, okay, I can do get the programming right. What's pseudo king? Turns out it's about 0.7. What's it? 0.7 is 707 square root of 2, 45 degrees. So those two vectors line up to about 45 degrees. I'm going to show you that that is actually, in this case, super amazing agreement. And I think next picture. 45 degrees doesn't sound like it's very much aligned, but remember, we're not in 2 dimensions, we're not in 3 dimensions, we're in 300 dimensions. And so that hypersphere is immense. One of the things that I did was I said, well, how does this compare to nearest neighbor words? And this is sort of a trick that I've been using. And I don't, how do you pick the words? What's the best way to do something when you don't know anything? Randomly, right? So I just take a bunch of random words and I compute the dot product with those. Here's about 50 of them, I think. I can't remember how many I used in this graph, but what's striking is that if you look at in this top graph here, look at the pattern here. The red is king, and this is king overlapping. These are the words that I kind of collapsed them, but these are all these words down here, all their vectors. It's like the word 2000 or the word included or the word published, and the pattern is pretty damn good. And if you take the word man, so that's our root word. Remember, man plus queen minus woman. If you take the word man, you can see how far off you are. It's a pretty big difference. And so this is sort of a good way to get a better test. It's not in an abstract vector space where you don't know what the hell the axes actually mean. These are actually just different words pointing different directions in this big dimensional space. And you can sort of see how's this pattern work. And that's sort of a nice way. You can compute a kind of a goodness statistic from that and some other things. I'm not going to go into all that detail, but it's a pretty nice way to look at word vectors. And so that's just a little trick. I don't think I have that code in the example here, but it's super easy. I mean, it's a trivial thing to do. So let's talk about why 45 degrees is a good thing. So remember, I'm an ex-physicist. So that implies a certain amount of torture. This is it. So if you think about, remember, we're 300-dimensional sphere. What does an angle theta mean in this sphere? Well, if you talk about a two-sphere, the ratio of the arc of an angle theta to the circumference of that sphere is just theta over pi, all right? But as you go into higher dimensionality, the numbers change quite a bit. So theta, remember, theta is a small number, is to the n. So think of 0.1 or point to the n, and then over 2 to the n. So this is, this sphere is just huge. And so even a 45-degree angle agreement between vectors is, statistically in the space of all possible vectors, hugely significant. And that's something that's not, it took me a while to figure that out. So I drew a picture and looked up some math on Wikipedia. I can't do this stuff anymore, but it's a pretty astounding result. And man, doesn't it look cool with the kind of like pseudo chalk stuff? And that took longer than actual math. So diving into politics. So has anybody ever seen the movie Inherit the Wind? My God, I just watched that the other night. I saw this quote from Clarence Darrow, and I was like, I got to see that movie again. Recorded in 1960, and it seems like progressive politics. Isn't that scary? When I was a boy, I was told that anybody could become president, and I'm beginning to believe it. That's where we are today. So let me just talk a little bit about some of the work that I've done here. This is going to go fast, and it's not going to be very deep. But one of the things I did was I just computed candidate word vectors. So I took a bunch of the words that they said, I added all the vectors up, normalized it to unity, took the dot product, boom, angle. At first I was a little discouraged. I said, damn, these angles are small. Then I did that math and I realized it's okay. And but what you see, this is a little bit of the science that I did. It depends on how you compute the vector. So I computed under different assumptions and plotted this trend here. And you can see this is you can see Saunders, the angle is pretty small, 190 milliradians. And, for instance, the difference between Sanders and Trump is 260 milliradians. The difference between Clinton and Cruz is 220 milliradians. Well, that's small, but it turns out that difference persisted. And so the graph below just is a plot of different word selections and things like that, pushing farther out into the distribution. And you can see, near in, when you've got a bunch of very high count words, the differences are quite profound, and that's a repeatable trend over lots of assumptions and things like that. So I thought that was sort of an interesting piece of data science to do, and I'm continuing to work on that one. You can start to look at candidates in context. So I had a lot of fun playing with different words, and so this has a lot to do with how you do the regular expressions. And I don't want to bore you with all that detail, but one of the fun things I started to play with was this idea of where do the candidate positions end up relative to some hot button words like people, country, and taxes. And depending on how you do the analysis, you can end up with a situation like this, where you've sort of got the people and country over here, and you got the candidates sort of grouped in the middle between taxes. But if you change the way you stem the words a little bit, you can end up with this kind of a funny interpretation, which I think is sort of interesting. It says you could almost argue that this is the idea that you take a country, you add people to it, you get rid of taxes, and that's where the candidates live. I thought that was kind of a funny outcome, and I can you know, this is one of those challenges where you want to make sure you're printing exactly the conditions you're operating under, because these are, but anyway, this is sort of an interesting way to look at the data. And I think the approaches like this will promise to give us some interpretability to the data long term. You know, I hope you're not expecting huge insights here. You know, if you want a private opinion, I could tell you who's an idiot and who isn't. But you know, I looked at the way candidate positions varied, and I think this is for again the 100 up to the first 20 words of the candidates. It's a bag of words, vectorized. No filtering of the text. You know, the vector space had 1,200 roughly vectors from the unidimensional vectors, and you can see that you know, the idea that Sanders and Clinton minus Trump, it gives you Carlo Rubio, or what's his face, Cruz, and that I don't know if that means anything or not, but it's you can start to see what the you know, how these things lay out in the vector space. Yeah, I don't know what it means either, but it's just sort of, this is the one that worked out, so I thought it was sort of interesting. You know, it's sort of fun, and you know, what I'm trying to do is, but what I'm really trying to do, is to establish differences between candidates. That's what I'm trying to do in the meta picture, right? So I'm trying to look at how do these guys compare to each other. How can I jumble them up in a way so that I can create an AI to say, take what this guy got, filter it, take the AI, take what this guy says, use what he said, filter the debate text of that guy, match it, subtract the text from the other candidate, create a tweet response. That's sort of the vision that I have. Sort of the architecture I'm trying to work toward, and you know, and so that's the exploration I'm trying to do. How do I seed a Markov text tweeter based on vector interpretations of tweets? That's sort of the big picture thing. If you know, some of the things I'm exploring. So I tried to look at, well, what words align to candidates best. You know, it turns out not much interesting there. You get an answer. So this is just what words match best. I think there's a word to vec function along these lines. And you know, if you say take Bernie's first, here's 16 words. I filter the text for things related to just the word terror. So I look only for terror in the debates, and you end up with a bunch of junk, right? This is just, you know, we want to think, should, going, what, but. This is where the tokenization comes in, because it. I mean, those are all great matches from the vector space, but they don't mean much. I started, yeah, what is that? Yeah. Yeah, so maybe yeah. Yeah, so they don't have any semantic value, exactly. And so then so thank you. So that's actually a good suggestion. So that's why I'm glad I'm talking to professionals here. Really, because I'm like, what the hell do I do? But anyway, yeah, these don't have much semantic value. And so I can go farther down the list, right? And that's a good suggestion. You know, let's see, I can go to the word ISIS. So I go to the word ISIS, I start to get more interesting results. You know, troops, forces, people. You know, there's some stop words, they, them, soldiers. Starts to sound a little bit more like the stuff you would say in a conversation about ISIS, right? And this is actually exactly what you said. This is going deeper into the text, right? This is getting rid of the junk on the sort of the foam that's sort of floating to the surface and going deeper into what he says. You know, so what happens when you do this filtering? So here's a filtering Trump where I really use a hard filter, starts and stops with the word wall. And these are sort of the comments that I'm taking into account. This is how the thing works. So these are the things that some of the things that Trump said that had the word wall in it. And yeah, it's pretty funny. All right, so let's keep going. So what happens? So one of the interesting things I found, if you take the differences between candidates, so you take the candidates, you subtract one from the other, and you filter the text for the word, in this case, wall, what do I get? Well, it starts to sound sort of interesting. It gets rid of a lot of the stop words, probably because the stop words all sort of float, maybe because the stop words are all floating to the top. I don't know. It's interesting to understand why the stop words are gotten rid of. Yeah, I like this. I like this.
If I had to guess, my understanding of the way those word vectors work is they're basically training a model to predict word based on context.
Yes.
And with some variation on that.
Yeah.
And so stop words are going to basically be predictive of everything.
Yeah, exactly.
Everything tastes like chicken.
Yeah. Okay. Yeah. 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 See? And I thought, yeah, that's great. So that's perfect. That's totally worth all the work to put these slides together right there. and this starts to sound interesting, right? I hope there's some funny ones. Well, maybe derivable, but they're like junk. It's like whether you cook chicken soup or okay, they're not junk, but it's like oh, I see what you mean. Yeah. So one of the things actually I found that empirically just in this analysis. So when I would take the word, for instance, terror, when I did the word analysis, I'd want to get rid of the word terror because it was everywhere, right? Yeah. Okay. So good. All right. So I'm justified in doing that. That's good to know. Actually, in here. It's not really a stop word, but it's the pervading context of the whole conversation, and yeah. So anyway, and you can see here, for instance, here I just dumped the first 5 words of the list because they were non-meaningful in this context. They contained word wall and the word whatever, and so but you can see here that Trump and Cruz, if you look at the word wall, you get differences like stuff, border, refugees, guys, Sudanese. Refugee, Rwanda, it starts to sound like the conversation they're having. And you could totally make, if you wanted to do a Trump response to Hillary, sorry, I'm going to say this, but so funny, you could make a totally racist tweet out of this, and it would be perfect, and, and it comes right out, it comes right out of what they're thinking. I mean, that's a funny thing. And so, I didn't, damn it, I had some really funny ones. I don't have them in here, sorry. I guess I'm to the conclusion part. So what I want to do now, I'll just kind of hit this conclusion thing, and then I was going to show you some of the code that I use just to, it's not great code, and I could use some pointers. But the speech is strongly distinguished by bags of words. I was actually surprised that I could see differences. And another interesting lesson is, if you look at the debates, the first thing I thought was, oh, this debate's about the economy and this one's about terrorism. And they're going to be different words. No, these guys say the same thing. Doesn't matter what question they're asked, right? And you can really see that in bags of words. Pre-computed word vectors are pretty dang cool. I think, you don't need to go out and spend the $50 at Amazon to compute your own. You can do this yourself. I was surprised at how much tooling I needed to build to do this analysis. I probably wrote 30 little functions to just do different things that I needed to do, and it was sort of fun. R is great for that stuff. I mean, and then you can start to see differences in speech. I'm not a pro at this by any means. I'm just trying to get to an objective, but deconstructing political speech definitely feasible. And I really thank people for the pointers tonight. Where am I going? Well, you know, I'm continuing to explore code, so I got a lot to learn about I'm going to start getting rid of stop words and being more aggressive there. I mean, I got some pros here saying I can do that, so I'm taking that as permission to go ahead. And, you know, yeah. Oh. Yeah. I want to run it both ways. What I want to do is use this stuff to sort of get the meat of what I want, and then just use a Markov chain to generate the speech that's seeded. Yeah, and you know, is AI possible in politics? No, but we're going to have fun with it anyway. So that's sort of the conclusion of the prepared version of this thing. And I thought what I'd do is just sort of go through a little bit of the code. I haven't, oh, go ahead. You know, I did not, but that could be interesting. Yeah, that could be interesting. You could definitely, I mean, you could detect some, I mean, depending on what you were looking for, it would be possible. Yeah. Yes, I use the TM package. Yeah. I'll show you what I did. So here it is. Let me see if I can, oh, this is probably good enough. So this is, I write in the RM, you know, I like to have text in the middle so I can, you always write, what is the thing? You're always writing code for two people, yourself and your future self. So I always like to add a lot of comments. So let's go through this, and I'll just show you what I do, and you can give me feedback on any parts of this because I'm a hacker, not a pro. Okay? Can you guys see this? You're going to have to tell me what to do here to do that. Is there a way to do that? Oh, zoom in. Okay. How's that? Much better? Yeah, it's actually better for me. I think I'm going to leave it like this. All right, so here, let's go through this. So, you know, this is just standard stuff here. I got a few little things. I always throw my HTML stuff up in. Do you want me to run this first so you can see what it produces? Why not? Yeah, I know. Especially because the last time I looked at this thing, I was drinking beer over at the Rogue. So, yeah, it is running. It'll pop up in a minute. It takes a while to run because it's got to. We'll just let it go. So anyway, I throw all my HTML junk up in the front, and there it is. So here it is. So I always put a summary, data sources, and methods. I like to throw some code in. Here's one of the tables. I think this is filtered. Yeah. So here this is a filter build. So I'm experimenting with the word wall right now. Okay. So and just the word wall. And so this takes that word vector table I showed you, and it's reduced down a little bit. My sums aren't quite working. I don't know. I got to fix those, but. You know, it's sort of interesting. Wall, right? Mentioned by everything but Carlo Rubio. Who knows why? You know, but this is one of the challenges: is that there'll always be a candidate who's like, you know, an exception. So you got to write a lot of error handling, and that's one of the problems I faced. But you can see, you know, Trump. So these are some of the words that they say. This gives the vocabulary data down here. Here's the heat map of that word. You'll see that. I'll show you in a second. You know, I'm getting this warning because I forgot about that. This is loading the glove vectors. Here are some of the words. Here's some of the vectors. This is the plot of the vectors. And I actually have also a plot of the delta from the mean because there wasn't a lot of signal in the thing. The delta from the mean doesn't say much, but it looks a little cooler. Here's that data that I showed you earlier that I did a trend plot on. And then here's a bunch of some of the things. Here's people, country, and taxes. This is sort of one of the standard things I do. This one doesn't come in too well. Country and people line up here. Those are the two vectors I use to align the principal components. And then I compute the variance from those. And so these guys are close to people, pretty far from tax, not surprising. That's usually the way it ends up. Here's Trump and Saunders, just looking at, how do the candidates, if I line the vector space to maximize the difference between those two guys, how does everything else line up, right? In this case, there's not, they're at a 45 degree. What that means is that there's zero information there. That's exactly what that means, and not much information there. We start to look at word, this is the word frequency tables. Here's Saunders minus Trump, and you can see some differences there. I've thrown away a few of the first words, the top junk that drifts to the top. And anyway, that's what that code looks like. And here's, oh yeah, this is the funny one. I looked up the pairing of cruise minus the word friend. And what comes to the top? Boyfriend. I think it was funny. So lover. Anyway, I think it's sort of funny. Anyway, that's sort of where this that's sort of what this is what this code produces, right? Just one of the things that I did. And so let's go back to what I hate. View. See, is it view that I want? Source. That's what I want. And so let's go through. We can go through and just sort of show things. So this is sort of how I do things. I try to keep all my code chunks and descriptors. So the first thing I do is I go through my debate files are just stored. These debate files are too big to like sync with GitHub, and I don't want to pay the large file thing, so I just keep them local. I was trying to work out a way where I could go out, grab the zip file, rip it open online, grab lines, and bring it back in. Anybody knows how to do that? What's that? No, I don't want to use Dropbox. I don't even want to grab the file. I just want to go out and read the lines within a zip file that are out on the web someplace. No, the word vector. The word vectors. The debate files are nothing. The word vectors are like, yeah. Word vectors are massive, and so sorry. So I was speaking incorrect. So I'm sorry. I was wrong. So these are the debate files. So I just have them on a thing. I just go in and they're titled. So I just grab the titles. And then I load them. I load them. These are a bunch of the local functions that I wrote. Loading debate text, candidate text. Multiplot, vector normalization, just a few functions that I've stored locally on my, they junk up your code when you get a bunch of these functions, so I like to throw them into a file. The libraries are here, getting the text files. I think this is pretty straightforward. Yeah, I just, use a simple, the file name's in the list of Republican files, you grab it, and, I've been slowly shifting all my stuff to using these pipes because it just makes the code so much more readable. And I don't know, Scott, you want to tackle that one? It's just a program. It's intended to communicate between people and machines. Is it another programming language? It's a programming language. So anyway, yeah. This is pretty straightforward stuff. And so let's see. Let me go down here. So I keep my filters and my words, candidate word frequency. You want to look at heat map. So here's the heat map. And this probably isn't going to help you too much because it's all my, All right, well, let's just look at the ggplot part of this thing. So, a lot of the trick is getting the data into a format where you can actually plot it like this. Okay, that's the hard part, actually. Once you get it there, the plot works. But this was pretty straightforward. So, ggplot, here's the data file, and I use the words as a factor on the x-axis and the candidate frequency, it's called candidate, on the y-axis. The geom tile is what I use, and you just color it white, the white, so you don't screw up the tiles, and then you fill it. And I just picked some colors here. The midpoint, I messed around with the midpoint quite a bit, but the best thing worked out to be taking just the maximum and dividing it by 2, putting it right in the middle. I assigned an NA value, but it never gets used, and then that's really all there is to that heat map. There is let me see if there's anything in here. Yeah, this is actually pretty simple. I just let me see if I can think what I'm doing here. Oh yeah. What I do for each of the candidates is I basically am normalizing those frequencies, and then you just use the reshape. I just melted it. It's just as simple as just melting. Melt worked great, actually. And what's that? I know. Actually, yeah. Okay, you know what I'm going to do right now? Use dplyr. Okay, there's the comment right there. Yeah, and thanks. And actually, yeah, we just had anyway. Yeah, melt. I'm now getting rid of it in all my code because I was just at a talk this week. We got lucky, and Hadley was in Santa Clara for some of the user group thing, and he gave a talk at our group, and he was like, "Nah, I don't use melt anymore. That's like old school shit." And so now he's using something else, and so I'm trying to get to that. The dplyr would work good. Thanks. Yeah, and then I don't know. Let's see, loading word vectors. So this is what my word vector loader looks like. I just pick a number of words I want to do. I use close to if you go to 10,000, it starts printing scientific notation everywhere. I hate that. So I do keep track of how much time it takes to load these things, just because it's a pain. One of the things I like to do is always include in a comment what you're actually supposed to get when you run the code. So the first few words of the word list that you get out of the vector is already it's just a bunch of stop words, and yeah, pros, yeah, and so yep. Let's see, we can go through. This is sort of one way to calculate a vector. You know, this one I didn't fix yet, but I wrote you just take a graph, you find the word in a column. That's one of the differences I find is that depending on how I do it. So if I get rid of the $sign at the end, for instance, on the word tax is a good one, because if you get rid of the $sign, suddenly you get tax, taxation, taxes, taxee, taxer, taxet, and it changes it changes a lot the results, and that's it's subjective, but it seems to point in better directions often. So those are some of the things that you do here. I did write a function called vectorize, which later on. So this is vectorizing wall, and that just takes the word wall. Doesn't take anything associated with it. And then I have a bunch of computing standard vectors. These are some of the words. I just found it simpler just to compute a bunch of words. And so fear, you vectorize the word and then you normalize it. And that's what I've done to all these things, right? So that worked pretty well. And that's how And you can, I play around with a lot of these things like compassion. It's sort of funny to see how compassion lines up with these guys. And that's sort of it. Let's see, there was a place in here where I was having some problems I wanted to get some input on. Here's the idea, that when you pipe something, there's an assumption that the first element of the function is the thing that's getting piped to it. And a lot of times the way our functions are written, it's actually the second element of the function. You guys ever run into that problem? Oh, is there a trick? God damn, see, that's why I love coming here. What do you do? So where do you put the dot? Oh. Okay, I got to look that up because I wrote a bunch of functions to like say, okay, I want to put this in the third thing, so use thirderizer and you flip the order of the variables. Okay, if I look up pipe operator dot or something like that on Google. Okay, I don't even know who that is, but. Okay. I know exactly. Yeah, exactly. Yeah, that's how. I mean, I was like, hey, I know how to do this. How is? Oh yeah, I've done this before. Yeah, exactly. Yeah. Okay. That's good. So dots. Okay, I'll look that up. That's a big help. Yeah, there's someplace. Anyway, this is what the code looks like. I'll put this on GitHub. If anybody, I'll put this in the PowerPoint on GitHub or whatever it is. I'll put it as a PDF on GitHub if you guys want to. You can have any of this code. It's obviously open source. And I don't know. That's sort of it. I'll be happy. Take me probably about 6 months to get my Twitter thing going. The election will be over, but I'll be tweeting like mad. And yeah, but that's sort of my plan. So the next thing I want to do is get that Twitter. With Tay, the Microsoft Tay thing, and the competition's out there. I gotta meet it, and so that's sort of the goal next. Is do that. Okay, thanks.